Hello, my name is Victor Moreno. I'm a product manager in the cloud networking team here at Google Cloud, in charge of solutions, and I'm going to share with you a little bit of what we do with the network to support AI/ML and some of the mechanisms that that are in play when you start doing these things yourself. So we talked a little bit about self-managed as well as things that are delivered as services in Vertex. The driver behind all of this activity and innovation is very clear. We're moving lots and lots of data around. The models are growing, at what's actually starting to look like an exponential curve. So these are not models that are going to be crunched in one TPU, let alone one host. It's going to be thousands, right? So when we form those networks, there's a lot happening there. And you can't really create multiple copies of this and provide resiliency by having an active and a standby and a shadow or anything like that. So we're basically going to be storing a lot of that. So we have a couple of networks that we need to build when we're doing these things. So we'll talk about that and what are some of the technologies that play a role in all of this. For us to enable large model training, a lot of what we need to do in our network is accelerate some of that software-defined network that we've put in place, right? So the way we scale our global network is by basically getting a very robust infrastructure with a lot of capacity, but on top of that, we need to abstract it with an SDN. And a lot of the functions in that SDN need to be hardware accelerated. So I'll talk a little bit about the offload engines that actually do that for us and that allow us to get the GPUs to talk to each other at line rate, as well as the TPUs. We also have some interesting challenges with load balancing, and I'll show you a demo on how we're actually able to get better response times out of different models that may be running parallel to each other. The data center network, again, the infrastructure, what's underneath is critical, right? So we can abstract all day long, but if we don't have basically the hardware that can do this, and we don't have mechanisms by which we can actually restructure the topologies in ways that would actually play to the traffic patterns that we're trying to support, then we're kind of dead in the water. So lots of really good innovation there. You heard a lot about GKE. One of the things, once you are using GKE, one of the things that we need to be able to do is to have those pods actually have access to multiple networks in parallel. Right, so we talked about A3 and how A3 has more interfaces. Well, the reason we want more interfaces is we want more bandwidth. We need to be able to use that bandwidth concurrently. So GKE multi-networking is key to this whole thing. And last but not the least, not everything actually resides next to the cluster. We need to bring things in. We need to bring data sets. We need to get models from, God forbid, other clouds. And basically, there is a lot of data that is actually moving places. So the cross-cloud network allows us to do that in an efficient manner. So, the right questions have been asked in earlier sessions. Where does Vertex play versus the things that you do directly, right? So you can basically use the raw tools of how you manage the compute instances and actually create the network, etc. You can leverage GKE for some level of automation abstraction and grouping, or you can go all the way to the far right where all these things have been done for you in Vertex AI, and there are services that will do different things. And you can then create an application based on that. So depending on how customized the application may be, you may choose to be on one end or the other. In the limited time that we have, I'm going to focus on the left side of this for the most part. So let's start with training. When we train, as we shared, we're dealing with a very large number of variables, and we are basically creating neural networks that are going to span a multitude of nodes. If you think of the dashed lines of showing basically a node, in each node, you have a multitude of GPUs or TPUs. You have a couple of CPUs usually. And there are two patterns that we're going to be supporting, right? The TPUs or GPUs are going to be conversing with each other. They're going to be passing weights, parameters, whatever calculation is happening there. Sometimes they skip nodes. And that needs to happen with as little latency as possible and with the highest throughput possible. And that's a network that we built, right? This is a GPU to GPU network, or in the case of the TPUs, we basically put them all into a 3D torus, and it's basically a much more bandwidth capable network. But in any case, you have that red network that you need to provision. The other task for the people who are building infrastructure for these purposes is to actually create a connection to the rest of the world. So once all the number crunching has happened, now you have some conclusions, you have some weights, the model is programmed. That needs to be saved periodically to storage, right? We don't create 2 of these clusters. I don't think anyone can afford that or would want to afford that. So you have one cluster that is being trained. Every 10 or 15 minutes, there is a snapshot taken. Okay? And you can imagine the size of that snapshot. So we do everything within our power to keep these things within one class inside the data center, basically one network where the latency is the same between any pair of GPUs. The same thing should happen as we go towards the storage. Keep it in the same region, same zone. So the storage conversation is yet another network that we build. So think of this as a tale of 2 networks that we're actually putting in place. The network on the north side is more of a more traditional, if there is such a thing in cloud networking, but it's more of your standard cloud networking network, and those are basically the set of interfaces that you have on the north side. So this runs on big pipes, right? And what we've built in the data center for that GPU to GPU network is basically a class, non-blocking class. It's either in the flavor of 100 gig multiples or 200 gig multiples. And as we combine these things, we found that we need to be able to actually create flexible topologies. So we combine the electric switching with optical switching. And it's pretty nifty. You have basically a set topology, everything is already cabled in. And then if you want to create subtopologies, you move a few mirrors. And then rather than repatching cables, basically the mirrors are reflecting our signals and creating these topologies. And there you see a green one and a blue one. And it's a little sci-fi-ish, but very high capacity and very flexible.
So I want to make sure I understood what you just said, because this is networking and it's cloud field day. So the same cable plant, same optical cable plant, but basically different wavelengths. So I can, when I'm doing the east-west network, that's separated out at these speeds, north-south separated out at the speeds that are typical for traditional north-south network.
That's one part of it. Also for the east-west, right? You would create subtopologies. Part of it based on wavelengths, but a big part of it based on the same wavelength being reflected in different ways, so that you actually connect a different set of switches together.
So the physical connective, so the cable plant is variable based on the use case.
Up to a certain point, right? So think of this as you've got machines, you've got the first line of switches, second line of switches, then you create the variability. When you're dealing with TPUs, we can create different types of topologies to serve better data parallelism versus model parallelism. The torus will vary there, and what we do is we basically connect directly to the optical network.
Okay.
But the TPUs are basically all wired. We don't send a poor soul there to go rewire things because you did a reservation with DWS 3 months ago, right? We do send a poor soul to install more stuff when that reservation happens. So that's a different problem, right? So that's the physical plant. As you can see, it's highly programmable. It doesn't get programmed on the fly. I mean, you provision a cluster, and then all of these things move, and we get it going. But then the next thing that happens is once you have this all set, then we run a software-defined network on top of this. And if any of you have looked in detail at software-defined networks, there's a lot of tunneling that takes place there. There's a lot of things that we do to packets before we put them on the wire. So it's not just you hit the driver and you're off to the races. Before you hit the driver, a bunch of security, networking, and storage functionality and tweaking happens. And for that to happen at line rate, we basically offloaded to the NICs. So that's what we had done up until very recently. And we now have expanded the ability to offload a lot of that functionality to have also compute power that is beyond the NICs in our infrastructure, which we call the Borg infrastructure. Now, you may be wondering, well, why is this interesting? So we talked about creating a couple of networks, one to access mainly the storage and the outside of the cluster, and another one for cluster-to-cluster communication. When we're accessing storage, in many cases, if you have a big enough job, you're going to have to over-provision your compute and dedicate CPU cycles to handling the write to storage. We could try and offload some of that to the NIC that is on the compute, and that may still not be sufficient, and you may still find yourself over-provisioning this. Now imagine you're paying for GPUs more than you should because you need CPU to actually write the results onto storage. So in order to avoid that, we basically have further offloads that allow you to actually do the crunching that you need to do to write to storage in the infrastructure. So these offloads are critical to that yellow network that we talked about. But they're also critical to the red network, right, which is the host-to-host network in the training set. And what we do in our overall, what we do for networking in Google Cloud is basically we have that off-host processor actually has all the information on how to forward traffic between any two endpoints in that fabric. You will send the traffic to that, and that will actually send the traffic on its merry way until you identify, or the system identifies, that there is a flow that is long-lived enough and has enough juice in it for us to actually write the reachability information into the endpoints, right? And then you shortcut communication directly between them, right? So the result of this is very large scale, but also very high performance. None of that forwarding information is loaded onto your compute. So your computers don't have to think about this. So a little bit like an application service mesh where basically the sidecars are actually doing all the work. That's basically a hardware accelerated version of that in the SDN.
So for the GPU network, is titanium and offload happening there as well?
Yes. Yes. Think of it, GPUs accessing the NICs, and they talk directly through this mechanism. And I'll go into that in a little detail. Actually, I think that might be the next slide. No, well, not quite, but it's getting there. So, well, you've seen a more detailed version of this. We're going to be talking about compute form factors, and I'm going to use the A3 Mega as the example. Right? They all work in a somewhat similar way. The TPUs have a different way of doing things, but I think this would give you a good idea of what's actually happening in the process. So on the A3 Mega, we have basically the 8 GPUs, and we have 8 interfaces that are in place for the purposes of actually creating that GPU to GPU communication, or that GPU to GPU fabric. Okay? Each one of those interfaces is 200 gigs, so we bundle them. The bundle of 8 gives us 1600 gigabits per second. So that's the capacity that we have to get out of one node and have those 8 GPUs actually communicate with other GPUs in other nodes. On the north side of this, you see one interface that is at 200 gig. That's how we're going to basically do our backup to storage and access anything else. If we're serving with these devices, basically the serving queries will actually come through those interfaces. So the first thing that we need to do is get those GPUs basically wired towards those NICs. And they're not literally wired, but we need to get them to access the NICs directly. If you don't do anything, they will actually send traffic over a PCI bus to the CPUs, and the CPUs will then have their own stack, and that TCP stack will do its things at a slow pace and send things on their merry way. So what we do is we use GPU direct with TCPX, and in the case of the A3 Megas, it's TCPX-O. That gets us basically to have the GPU memory access a offload stack, network stack on the NICs that actually now has direct access to your network. We need to model those NICs as virtual NICs so that we can actually tap into the 200 gigs that each one of those NICs offers. right? So this is step one. Without all this innovation, we wouldn't actually get the performance out of the node. So step number one is get the traffic onto the wire. Now, we want to use 8 of these NICs. And as you heard, we're basically putting everything into a GKE pod for many reasons, right? We already talked about that for about a half hour in the previous session. But since we are in the pod, we need basically to have a multi-NIC environment for the pod. So single pod that goes to basically one network over multiple NICs. Right? And we'll talk about that one network because what happens is, because I have the multiple NICs, I am now mapping to multiple VPCs. So now I have basically 8 networks that I am connecting to, and I'll talk to that in a second. But we want to create that aggregate. Basically, what we're looking for is creating a bundle. You'll see that we create node pools, and each node would be dedicated to a single pod, at least for training. Right? That might be different for inference. We may actually have several pods in one node, but for training, we have a single pod taking over the entire node, and that single pod would have 8 virtual interfaces, each one of which we're going to map directly to the physical NICs. So it's a one-to-one mapping of the virtual construct to the physical construct, and that has to be terminated in a separate virtual network in the fabric. Okay, so we've got multiple VPCs now. Inside those multiple VPCs, each one of these things land in their own subnet. So now I have 8 subnets across 8 different virtual networks, and I still don't have like 8x the bandwidth. I just have 1x the bandwidth going to different places. Right. So the next thing that we need to do is this is my attempt at simplifying this, so my apologies. But the south side of the simplified diagram is basically showing those interfaces that are there for the GPU to GPU network. And as you can see, I have the first interface in each one of these A3 nodes I've tagged in blue. And it connects to a blue network that cuts across all of these different guys. So if I have 15,000 of these nodes, I have a 15,000 wide subnet or secondary address space that these things are connecting to. That is in VPC 1. And I do the same thing for the next interface and the next interface and the next interface. So I have 8 of these, right? The blueprints are out there that will build this out for you automatically. And then I want to connect these together. And basically that's where we bring the fabric together, where the virtual networks actually connect to each other with an abstraction that we call NCC, the Network Connectivity Center. There isn't a node in the middle of any of this. This is all talking, as we showed, from the offload engine to the offload engine. There's nothing in between. Very important. There isn't a router in between. This is going to choke. Okay?
And the data center, if we wanted to do something similar to this, we use something like EVPN to create this. But because there's no layer 2 in public cloud to be able to simply bond the NICs, you're doing this at an IP layer, and then you're using titanium basically to accelerate that overall abstraction of the IP to create these massive tunnels.
Yes. And if I may play that back, in EVPN, we're going to basically be using MAC addresses to communicate things with each other. We're going to have BGP as a control plane to decide where everything goes. And we're going to then tunnel with VXLAN between these things, right? The VXLAN acceleration happens on the switches, right? What we're saying is that we are going to use tunnels. We're not going to use BGP, but we're going to use our hoverboard control plane. And the tunnels that we use are not VXLAN tunnels. And things are, instead of using MAC addresses, we use, it's not even IP addresses, it's node IDs to actually forward between things.
Because we're programming an SDN that already knows about those IDs. Yes. This is all constructs to program the SDN. There's no actual...
This is just basically showing you, if you were to do this yourself, the abstractions of the SDN may actually need a little bit of petting.
So I'm confused a little bit on your terminology there. So all of those 8 VPCs and the 8 A3s and those NICs.
Yes.
This is all inside a single GKE node, or is this multiple nodes?
No. So
I don't understand the
yes,
outside box.
this is one physical node
That's one physical. Okay.
that hosts one GKE pod, which is,
And it's 8 GPUs in that node.
and there's 8 GPUs in that node,
Okay.
and there's also 8 interfaces that the node has access to. We map all 8 interfaces to the one pod. So just think of the pod as basically, again, it's an abstraction that we need to pet, and that's just one node that is connected 8 ways.
And it's the titanium PCIe card that's got those 8 ports that are plugging into
Correct.
to the physical switching.
Correct.
So in that case, you have, say, the first accelerator is connected to, on each node is connected to VPC1. The second accelerator on each node is connected to VPC2.
Yes.
And you have 8 separate VPC networks. And then you have an abstraction layer on top of that, which is your NCC that connects the 8.
Allows them to talk to each other.
So routes between them in some form or another.
Otherwise, the control plane is instructed to not let them talk to each other because these are segments that were put in place for all sorts of reasons.
Right.
Yes. So this is simply handling the fact that the physical interface as of a 3 mega can't be used in, it has to be in one VPC. And if the same node has another physical interface, that must be in a different net.
VPC. Gotcha.
So
Yeah.
obviously I'm creating some overhead with this. How much actual through? So I have 1,600 gigabits raw. How much am I getting from a practical throughput perspective?
From a measured practical throughput, I do not know. We are basically not adding any overhead because of the offloads, right? So you should get very close to the line rate, if not the full line rate. Yeah, and it also depends on, is it a TCP conversation? What's your good put? I mean, it's many ways of measuring.
Because this is all still where this is the equivalent of layer 2, just abstracted. So what you put on top of that might add additional latency.
Well, be careful. The scale of this is like orders of magnitude beyond what you can do in an.
There's no way in hell I would put 15K hosts in a single layer 2 domain.
Well,
but this is a different abstraction.
Definitely, I have to be in my old networking mind.
But yes, that is a really good anchor point. Yes, that is a healthy way of looking at it.
I think for Keith, I think the important point is when you're connecting all these VPCs together, it's not yet another layer. It's much more enabling permissions to crosstalk.
Pretty much.
And giving the routing information of how to get from one network to another.
Not even giving it, just saying you can access.
You can access these.
Yeah.
Okay.
You're allowed
what if one of the VPCs fails? Or does it have failover? Can it do like 2 or 3 or?
That is a great question. So what if one of the VPC fails? So this is all in the same region, which means all the control plane for the VPCs is actually shared, right? So I think if you have a failing VPC, and I'm not even sure what that would look like, you would have basically 8 failing VPCs.
Yeah, because it's essentially a database table where you look at how do I get from this node to this node.
Correct.
And everything that we're doing here is to map it into constructs we understand that aren't a database construct.
So there is some hashing that happens, and we do shard things based on VPC ID across different instances of the control plane. So half of them may survive, and the other half may actually get corrupted in that scenario. But that's a clear scenario in which I think the connectivity, so the effect of what you're describing would be I don't have connectivity over those interfaces, which basically translates to the job will stop, and then we go back to our backup, our snapshot, and then whatever the RPO is, if you're doing it every 10 minutes or 20 minutes, your RPO would be basically of that.
So just to be clear, to go from, let's say, GPU 0 on A30 to GPU 1 on A32 is no different than going from 0 to 0 on different A3s. I mean, there's no additional overhead to cross VPCs as there is to go through one VPC to another.
Yes, absolutely.
And just to clarify from my side, so you are mentioning there's a one pod running in on the single node,
Yes.
and you just said, pod is job. So like that pod is basically, like AI ML job, which I've just triggered, or is it like transit network? So if I will be running job, that job will be connecting into that pod, which is connected into the 8 GPUs.
I would think the job actually involves a multitude of pods.
Okay.
So it's just one node in a big network of neurons that are trying to talk to each other.
So then it's about like how I'm going to share the GPU, right, on the node.
Correct.
And then it's like, if I'm going to be sharing between multiple nodes, or if it's going to be one node connected into all 8 GPUs, do the job, finish the job, and then next pod is going to be started up by the job.
Right. And usually you quickly do some calculation and you pass on a subset of what you've concluded to the next node.
To the next.
And sometimes, depending on the flavor of transformers that they may be using, you would skip a layer. And that's where the optical network is interesting, because you could have those layer skips have bigger bandwidth than other communications.
So it can be like, I'm running 2 pods on one node, and one pod is connected into the 4 GPUs. And the other pod is connected.
For inference, you would do things like that.
Yes.
For training, you probably wouldn't.
Okay.
If you could actually model like 50,000 of these things as one node, you would. And that's basically what a lot of our customers ask us for on the TPU side.
Okay.
Give me a 3D torus that is like 65,000 wide and has this shape or that shape. And that's where the elasticity of the light wave network comes into play. I can go deep and narrow, or I can just be a perfect square. Depends on whether you're looking for data parallelism or model parallelism.
I'm completely out of my depth. This is cool, but out of my depth. This is.
We can talk about it at dinner.
Yeah. You can talk about it.
No. I'll be asking. You will be giving me the answers.
I think if you do it yourself, there's some considerations, but we are able to give you a fabric that is basically not compromised in terms of whether you're in one lane or another. Is it going to have different performance? It's going to have consistent performance.
Yeah, you want to have a predictable performance, right?
Correct.
This, like, you don't want to have a like up and down. You want to have a baseline. Like,
yes.
The last day or so, we were talking to another networking company, and they were talking about 2 back-end networks and 1 front-end network. And the front-end network was for slower, checkpointing and things of that nature. But the second back-end network was GPU to storage. And I don't see that here, other than it's a front-end solution as far as you're concerned.
We're saying you go out of the CPU PCI to storage.
But it's not a back-end network to storage. It's a front-end network to storage.
It's a front-end network to storage. Yes.
Is that 200 gig interface you were mentioning?
200 gig on each one of the hosts.
Interface.
Yeah. For
all 8 GPUs.
Yes. Yes, for all the state that you have in all 8 GPUs, 200 gig. That interestingly, that hasn't gotten in the way of progress. It is the bandwidth down on the south side that usually is the long pole. And that's a function of the size of the data sets that you're backing up and so forth, right? Also, the acceleration is key in not having to over-provision not just the channel, but the processing that you need to do to populate the channel. Now, that hits also our SDN, right? And in our SDN, we have access to all our storage services, right? And we usually abstract that as managed services with PSC endpoints. And when we do that, we want to make sure that we keep all of this in the same region that we have, so that you're not incurring like a 10 or 15 millisecond penalty because you're going too far away, right? Some region to region is in the 2 milliseconds range, but there's no reason not to keep it in the same region.
And that 200 gig link that's coming off the CPU is also accelerated with titanium, and you get the storage acceleration out of that titanium.
And with the titanium that is off host that we talked about, right? For the storage
the Borg and
yes. And one thing that we've noted is that, or we noticed is that as you bring in models from other sources over your, and on the top right side, I'm showing connections to the outside of the cloud. As you bring in those models, we usually load them up to storage buckets. You don't actually have that be loaded directly over those load links. You bring it on storage buckets, and once it's all in place, then you run your training job, right? It's too expensive to just wait for that to slowly trickle in, right? And it is a fast connection, but it's a lot faster when you're in the region, right? So think of the storage as basically the intermediary backups, as well as any data sets that we use for training and so forth. Okay, so this is just a summary for you. I think we're probably running over time. How are we doing?
Yeah. We can move on.
Could you bring
Okay.
back the summary slide again, just for a second?
Okay. So move on topic-wise, or move on to the next presentation? On the inference side, we basically assemble these applications, and we have a well understood set of practices on how we actually create a web application. Well, this is far from a web application. We've gone from small requests to very large requests. We've gone from actually sharing the CPU resources to basically taking an entire node to actually service the queries. Requests get queued. Normally, requests just get processed in a web application right away. Processing time from seconds to minutes versus instantaneous responses. And, caching is not a thing, right? When you ask Gemini about something in particular, your question is unique in its own right, the answer will be unique. So we're not caching those things. So it's a very different experience, right? And we have to do things in slightly different ways. Now, one of the things that came up earlier is, well, you have all this infrastructure and you have vertex, right? So how do these things correlate to each other? And what you find is that all these models combined, and as you build the services, one of the things that we do as common practice in cloud networking is that we bundle these things as managed services, right? And the question is, who manages it? Either it's a group within your organization or it's a different organization. In any case, the way this is exposed is the service is basically a multi-instance service, usually, to actually handle the load. We put load balancers in front of the services, and then those VIPs are actually exposed by something we call PSC. And think of PSC as a mechanism by which you can actually access an API no matter where it is in the cloud organization. So whether it's in your own project or in a different project, you can actually access that API through private addressing, right? So that combination of the load balancer and PSC is what we are basically referring to as the model as a service endpoint, right? And when we assemble applications, the way we do the networking is we basically point to different endpoints. It's an exercise in calling APIs. From a network perspective, it's all abstracted as endpoints. And basically those map to DNS, and that's how the names actually become connections, right? So with traditional applications, that's what we do, and then with models and other types of services in AI, we're basically doing a similar thing, right? So the beauty of this is that it allows a clean interface between the creators of models, between the people who are actually there crunching all these numbers, and whoever's going to consume it, right? So the consumer basically connects through the PSC endpoint, and the producers simply create what they've created, and then there's a load balancer that is actually exposed and published to be consumed this way. Okay, so it's a clean interface between producer and consumer.
Private load balancer that's behind the PSC, and then there's a public load balancer that provides the accessible.
And you can, yes, and then you can load balance the PSC endpoints in their own right?
And can we do routing for different requests through that PSC and load balancer, or is that a normal pattern?
Correct. No, you can tweak it whichever way you want, and we'll talk a little bit about some of the interesting things that we do there. So within Vertex, right, what you will find is that we have different model instances and so forth, and we've basically put a load balancer in front, and then when you consume a Vertex service, you're really connecting to an endpoint that is exposed either over PSC or PSA. There's variants there. We're not going to get into those details, but that's how you consume the Vertex service, right? So the load balancing inside of these Vertex services is already model aware. And there's some interesting parts of that model awareness, but we can actually create affinity between the client and the model. So as the requests come in and they're coming from a particular client, I'll have multiple instances of the model, and I can attach to a particular instance and keep that consistent. We have service extensions that we can use to actually program functionality in here. But the more interesting part is that we have metrics that gives us the utilization of the model and the depth of the queue of requests. And based off of that, we can optimize the latency that we get as we basically service requests across multiple instances of the model. So the way we do this, there's an open source framework where we have open request cost aggregation, so we call it Orca, and we can basically have standardization of values like queue depth and basically load balance based on that. Right. So when you do it yourself, what we're releasing is basically your ability to use similar load balancing features in a model that you may have built yourself over GKE. So remember, we could consume it from Vertex or build it yourself with GKE clusters, and then we can load balance and expose it as a service. Right? You create your own service, and then you can leverage this type of load balancing. So let me show you a little bit.
Is Vertex auto scaling based on demand and things of that nature?
Yes, within the service. Right?
Yeah.
And that's how we optimize the response. So let me show you a little bit of this this demo that we have here. So if I create my own Vertex equivalent service and I just use standard rate distribution in the load balancer, you'll see in a second the kind of response that we get. But you can see there's 4 queues there. I'm trying to distribute this across 4 different models. There it goes. And the 95 percentile latency keeps growing. It's like at 6 milliseconds going, it trends all the way up to 7, and you can see how the queues are very uneven. Right? Those are requests that are queued, right? And they get serviced within 7 milliseconds and so forth. If I add the custom metrics that we actually can get through Orca, we can basically use queue depth, and we say set a target value of 2.5 milliseconds. And when you run that, the result is drastically better. Right? So the queues are basically now kept at 1 or 2 requests consistently, and the 95 percentile response time is basically not to exceed a millisecond and change.
Are we getting the same request rate coming in from the outside of this?
Yep.
So what's the cost associated with that? I mean,
The cost.
well, I mean, we set a certain standard, which is great, but I mean, there's got to be something that is, I mean,
The
some
trade-off.
sort of trade-off. Thanks.
Yeah, what's the
What are we?
what's the engineering trade-off?
What's the
Of course, it's
Yeah.
Well, so in terms of the network or in terms of.
So one case you're using a Vertex solution, the other one's a do-it-yourself.
No. They're both do-it-yourself, or imagine that Vertex had done it without the queue depth parameter in the load balancer. So the load balancer had no knowledge of
So all
the utilization
queue
of.
depth as a metric to optimize.
Correct. So by doing that simple thing.
I still feel like I'm missing something in that suddenly these 4 servers are responding so much faster because I send requests to them in a different order.
No.
The load balance is working correctly.
The load balancer is working correctly.
differently and
It's
better.
setting them in the right distribution to make it more
well,
efficient.
it's not just that. It's
But
it's probably auto scaling as well, right?
No.
No,
it can't
There was no scaling, there was no change.
So how come it's just responding faster? Just because if we
Ray.
Request
No,
at
no,
the right
the individual-
place at the right time.
So the individual servers response at the rate they respond, and it's not just one server, it's the model, right? So if the model is pending responses, you're not going to send more stuff to just get it queued there. And what's happening is like the queues get overwhelmed in one side or another. So it's almost like going to the supermarket and do you actually have everyone perfectly go to the optimal place where the queue is about to empty versus we're all going to go here and now there's a head of line blocking because I can't go ahead of somebody that's behind me.
So
It's the difference between there's one line that you get to the front and the next cashier is yours versus everybody's in their own line and you're guessing which one's going to be faster.
or
That's what's happening.
or you got the guy who's going to pay with pennies, and you're like, oh, but I've stacked the load balancer is doing what it's supposed to do, which is to stack jobs equally across the thing. But if the guy with pennies slows up a server, then
Right, but that affects the one line. The load balancer is more accurate in that case because it's taking into account how many people are in each line before it sends another one over there instead of just saying 1, 2, 3, 4, 1,
Right,
2, 3,
exactly.
4.
What wasn't visible was that quite a lot of the time, 3 of those 4 nodes had nothing in their queue. We didn't see that in the numbers, right?
The
We
other
saw
one
an
had 9 or
average
10.
number over a second, not the actual queue depth. We saw the number of requests that
Yeah,
were outside.
it's a very old load balancer problem.
Yes. Yes, it is. But
So-
that's
So am I missing something? Why not just turn that on all the time? Is there a reason not to have that turned on?
well because we're learning as we go, right? So those are metrics that weren't necessarily available
And
all
Vertex
of the
turned
time.
it on.
Yeah, and then we turn it on for Vertex, and now it's like,
That-
okay, guys, people are doing this themselves.
Okay,
Why can't we expose that API? And now the API is exposed.
okay.
So
Are there other load balancing
the
inside
Orca,
of that queue?
the
Is that queue?
there
that
is-
we
there
think
is-
appropriate in a
there-
different workload, I guess is what I'm asking.
there are things that are in Orca that we could actually start leveraging. So this is step one.
Okay, so that's just
many
an
things.
example. There could be a different load balancing algorithm that might work depending on a different workload.
Correct.
Ah,
Yeah. Different
okay. That was
parameters.
the missing
Yeah.
piece. Thank you.
Yes.
And if I'm understanding you correctly, you're basically saying that instead of manually looking for and managing these things, the Vertex product
Yeah,
is learning from all that's been happening and it's taking care of this for us. That
Correct.
that it's just
It's
doing
in
it.
the Vertex
So
product.
you don't have to remember that class you took in F5 10 years ago and that you did your
Well,
load balance.
You may have that luxury. I still have to remember, but yes, yes. So simple. Like we're basically using the load balancers and integrating model knowledge into the load balancers. Basically, that's what's happening, right? And you can fail over across regions if the models are being served across regions. You can split traffic across different models and test performance of one type of model versus another. You can do all the good things that we do in traditional applications, but we can do that basically in the context of AI applications. So where do we see things going? AI-assisted products overall in networking. So natural language support, not just to say I can speak to this thing and it's going to create a network for me, but to also to say that I can actually provide a diagram. Okay, this is what I want you to build. So my clearer diagram, ideally I'd be able to give that to the AI and it will basically build a cluster for you. And that coupled with intent-based configuration. So you've probably heard a lot about intent-based configuration throughout the years, and it just never happens, right? Because it's very hard to come up with an alternate language that is half human language and half computer. And we never seem to strike that. We usually fall into, okay, now it became yet another CLI. So the hope is that we arrive at something that is reasonable, that the computers can actually tap into and be more effective in their natural language conversation. So that's where we see things going. And of course, the data plane abstractions need to match those models that are.
Can you go back one slide, please,
Yeah, certainly,
just so we can get a picture of that.
certainly. And yeah, so and that was mainly what I had prepared for you. Hopefully, it was useful. I know you were talking a lot about compute and cloud, but this is basically what's actually happening underneath. So I'm hoping at least some of these sound bites help anchor things down into, okay, I get it, and this is what's happening. I always joke that we are in the business of skinning cats, and even though we're in cloud, the cats haven't changed. So, so it's
Interesting.
just really big cats.
You're saying that there is no cloud; it's just somebody else's cat.